Well, no, I could actually stream Netflix using my laptop and then putting the image of the laptop on the TV.
Uh-huh. Does it take up the
But
whole space or it chops it off?
it takes up the whole space. But
Oh.
I just don't want to support Netflix. I don't want to give them my money anymore. If they tell me I have to buy a new TV to watch them.
Oh.
My TV is only 10 years old.
Oh, I see. Yeah. Oh, I can send you the $20 Roku. So you don't have to stream it your laptop anymore.
Yeah. And the other thing is, it's not just Netflix, it's Amazon Prime, which I'm also a member of.
Uh-huh.
They also dropped support for my TV. There's a whole bunch of.
Oh, I'm sorry.
But now I have access to home crafts on my TV and all kinds of other interesting things.
Yes, yes. So then I'll find something that give you both Netflix and Amazon Prime, and then send it to your mailbox.
Okay.
Professor,
all right,
are you
let's do some math. Yeah.
Are you gonna post the final on Canvas today?
Not today, tomorrow I'm gonna post it. I know I said I would do it today, but I struggled with calculus today.
Okay, but so
and
you're not
pre-calculus.
Okay, so you're not
I'm gonna post it on Canvas,
okay.
and then it's gonna be in the assignments.
Okay.
Because if you upload it on Canvas, you can use that thing called SpeedGrader. After I'm done, but so.
I can't hear you anymore.
Professor shares the streaming with Mrs. Horn, and then her bandwidth is overpowering probably professors.
Oh, I see.
Sometimes. Hello? Oh yes, he's back. Professor?
No, I think he left. He left.
I think he got dropped.
Yeah.
So how are you?
Okay, how are you?
I got tested for coronavirus, and then it was negative.
Wow.
Yes.
You have to celebrate.
Yes.
That's good news. That's good news. Congratulations.
Yes. So Angela, you're safe as well.
Yeah, wow.
Of course I'm safe. I knew I was safe.
But weren't you worried? Weren't you worried that like very early in the semester, like March or February?
I was because I shook someone's hand who was from Germany.
Oh yeah.
But I don't have it. Yeah. If I did, I fought it off. I'm good.
Oh jeez. Yeah.
Oh, good news. Good news. Okay. Well, what is the test? Professor say I don't understand. What tomorrow he sent?
Yeah, he said tomorrow he's gonna put it on Canvas.
And when we have to back?
By next Monday.
Oh, okay.
We're in trouble.
How are your TA classes going?
Angela? Hello, Professor. Are you back? Oh, he's not back.
It's possible
he's back. Yes.
Yeah, I connected. That's just
Mm.
my Wi-Fi.
Mhm.
Okay, how was the reading?
It's very confusing. Long and long and technical.
This started confusing. Give me a page number.
Was page 267?
Yeah.
So they say the space of continuous function on a compact set K is a metric space.
Oh.
Hello? Hello?
Oh.
Can you guys hear me?
Yes, I can hear you.
Oh yeah, so page whoops, why is this? Page 267. They say this DFG sup of this one f of x
Mhm.
minus g. If we have triangle inequality, so f minus g less than equal to f of h, for example,
Yeah.
h plus h minus g, I guess. H
Yeah.
minus g. Do we get that? Can we do like h minus g? Do we put soup here and then it works?
It works with the soup.
Oh, okay.
It's I mean the triangle inequality, if you look at f of x minus g of x, this is less than or equal to f of x minus h of x
Mm-hmm.
plus, and that's for a fixed x, h of x minus g of x.
Mm-hmm.
This is less than or equal to the soup over x of f of x minus h of x
Mm-hmm.
plus h of x minus g of x, right?
Mm-hmm.
And this is less than or equal to the soup x f of x minus h of x plus the soup over x
Ah.
h of x minus g of x.
Uh-huh. And then?
And now you have a right hand side which is all souped out. There's no x's left, right?
No. It's constant. I
Yeah,
guess it.
right. And now you can take the soup on the left hand side. The
Yeah.
soup is bounded by a number, namely the
Uh-huh.
right hand side.
Right.
And that gives you the inequality for the soup.
But if you take the soup, then isn't it possible to have equal? Oh,
Yeah,
still it's
but it's
less than
less
equal is.
stable inequality.
Oh, yes, yes. Ah, okay.
It's a
I
non-strict.
see.
Triangle inequality is never strict.
Uh-huh, uh-huh. Okay, I got it. Thank you. Yeah, I was thinking, yeah, it probably should work, and then like need definite answer from you. Thank you.
Okay. And then
Oh, so the well separatedness on same page, Professor?
yes,
Well separatedness is just d of a b is bigger than 0.
yeah,
Okay.
that's the same as we had for the outer measure for the Lebesgue measure.
Yes. Yes.
For the exterior measure, we required that.
Uh-huh.
And if they are well separated, so a bit and so then mu exterior measure of A union B is equal to exterior measure of A plus the exterior measure of B.
Mhm.
And then the proof of theorem 1.2, if you look at that, and you look at the proof of where is it? If you look at
Equation 2.
theorem 3.2 on page 19
Mhm.
and theorem 1.2 on page 267.
Mhm.
And if you look at the proof,
Mhm. In equation 2 in the top of the page 268, they use the separation.
they use the separation, and
then the BK and then A2K minus 1, they use separation.
yes,
Mm.
and then they use the countable additivity for well separated sets
Mhm.
in the next two inequalities.
Okay.
But it is essentially a mirroring of the proof of theorem 3.2 on page 19.
Mm. Okay.
And proposition 1.3 basically this establishes the measurability condition from chapter 1.
Mm. Open set, closed set definition.
Yeah.
Yes. Professor, before proposition 1.3,
Yes.
they say Borel measures that assign a finite measure to all balls also satisfy a useful regularity property. What does it mean by the regularity property?
It means exactly what the proposition says.
Okay.
That every Borel measurable set, differs from an open set which contains it by a set of measure less than epsilon for any given epsilon.
Ah, okay. And Professor, in the proof of proposition 1.3, I thought that we're proving the open set O that does this open set O, and then the closed set F that
Yeah.
does this job. But then why do they show in the bottom of the page 269 the script C, the collection of all sets that satisfy this conclusion? So this script C is
It's a collection of all sets.
yes.
Well,
So-
this is another one of the proofs where you basically say,
Mhm.
you know, what you do is you look at the collection of all sets which are satisfied by the theorem, and then you prove that it's actually all Borel sets are satisfying the conditions of the theorem.
Mm, I see.
We had
So,
a proof like this before Fubini's theorem. The proof went like this. You know, let S be the collection of functions in the Fubini theorem which satisfy this property,
Mhm.
and then you showed that F is actually the set of all integrable functions
Mhm.
by some kind of density theorem, and that's the same thing they do here in this proof. It's actually it's a very nice way of proving things, saying that what you say, S is the set of something that property, let's say X, holds, and you show first S is not empty, and second S is everything. And you actually, it's a very familiar thing of proving things, because the principle of induction is based on that kind of proof. So this is more like a general principle so that it S is not right. And in the modern thing is you show that you establish this set, then you show first of all that it's not empty, and in the case of Fubini theorems, we showed that it holds for all simple functions. Simple functions are dense in the set of integrable functions, thus it holds for all integrable functions. It's just it's a very, let me call this it's a useful tool.
Yes, definitely.
Because I mean, Fubini, the traditional proof would be integrable, and we have to show application Fubini applies. And the other proof is the way we in the Fubini's proof went. Fubini applies to F. That implies F can be any integrable function. So that's an indirect way of proving things, but it's a very useful tool, and they use the same thing in proposition 1.3.
Okay, I see now. Sweet. Thank you.
And reading we had in this class. Now we had some problems, right?
Yes.
Exercise. So remind me about, I know number 5. Number 5 and what else?
Number 1.
Number 1. So let's start with number 1. So we have M is a collection of subsets. And we know that M is not empty. And M is closed under complements and countable unions of disjoint sets. We want to show that M is a sigma algebra. So for a sigma algebra, we need 2 things. Closed under complements and second, countable unions.
Countable intersection as well.
Now the intersection follows from the complements and the unions, right?
Yes.
Countable unions, but these countable unions, they don't have to be disjoint sets. So closed under complements, yes, we already said that. That's in the statement of the problem. Now countable unions, so suppose you have a countable union of sets AN.
Then you take the complement. Countable intersect. That's the complement of the intersections.
Yeah, the
Countable
intersection is just the complement. We get that immediately.
Right.
So all we have to show that it's closed under countable unions. We know it's under countable unions of disjoint sets. So we construct B1 is equal to A1. B2 is equal to A2 minus B1. And you go
We lost the sounds.
or guide. Can you hear me, Masood? Can anyone hear me?
We can hear you, but dropping in and out.
Yeah, drop. Now I.
Yeah.
Okay.
That's So Bn is, we take An and we take the union of all way. Then we have I intersect with Bj is empty. It's not equal to J. Everyone agrees with that?
Yes.
So the BIs are all
Disjoint.
empty,
Mhm.
disjoint. But
Mhm.
union from any 1 to infinity Bn. So this is B1 union A2 minus B1 union A3 minus B1 union B2 and etc. And so this is A1 union A2 union A3 etc. Is the union n equals 1 to infinity an.
Mhm.
So the union of the bn's are the same as the union of the an's.
Mhm.
Because in order to construct the bn's, all I took away values which I already accounted for in an earlier bn. And so you get the entire union, and we know that unions of disjoint sets are in M. So this is in M.
Mhm.
This is in M. And that means M is the sigma algebra.
Mhm.
What am I writing?
Professor, if possible, again, explain about close under the first condition. Why?
Well, it's closed under complements because the problem says that M is already closed under complements.
Oh, okay.
Yeah, there's nothing to prove. It already says that.
Yeah, this is the, okay.
The second statement is just uncountable unions of disjoint sets, and we have to extend that to any kind of countable unions. And to do that, we have to basically say that the countable union, any countable union of set, is a countable union of disjoint sets, and that's what this construction is.
Okay, thank you.
And it doesn't. So to show that this is over RD, that's of course not equal to 2, it's equal to 1. Sort of interesting. So we first look at the integral over R2. And what we can do is we can do a change of variables into polar coordinates.
Mhm.
And if we do polar coordinates, this is just a calculus exercise. And we get R, dr, d theta, and the theta goes from 0 to 2 pi. And so this is the integral from Fubini's theorem here. So which is equal to 2 pi, integral from 0 to 2 pi d theta, times the integral from 0 to infinity e to the minus pi r squared r dr. The 2 we put in front of the r here, and we erase it here. Sorry, I erased the pi too. And so this is integral pi times integral 0 to infinity. We make u equals to r squared, then du is equal to 2r dr. This is really a calculus problem. And we get e to the minus pi u du, which is pi times e to the, my stylus going out here, e to the negative pi u over pi between 0 and infinity, and at 0 it's 1, so you get 1, and at infinity it vanishes, so this is just equal to 1.
Yes, yes.
Then on the other hand, integral over r2 e to the negative pi, and now I'm calling it x1 squared plus x2 squared, dx1 dx2. We can again use Fubini's theorem. This is integral over r e to the negative pi x1 squared dx1 times integral over r e to the negative pi x2 squared dx2. But these two integrals are the same thing. So this is integral over r e to the negative pi x squared dx, whole thing squared. And this thing is equal to 1. So the individual thing can be either 1 or negative 1. It's certainly not going to be equal to negative 1, because if we integrate a non-negative function over the entire real line, we're not going to get a negative number.
Right.
So it is equal to 1. Okay, next page. With the same use of, if I take the integral over rd e to the minus pi absolute value x squared dx. This is integral e to the negative pi x squared dx over r, just like we did for 2 dimensions, to the power d. Each one are the same, which is 1 to the power d, which is still 1.
Oh.
So yeah, this is an easy problem. At least this is 1 for all d.
Oh.
Okay, that's part A.
Yes.
So part B is a little more complicated. If we take the integral over rd e to the negative pi absolute value x squared dx, we know this is equal to 1. And this we can write in polar coordinates again. And now polar coordinates is generalized polar coordinates in RD. So what we have in polar coordinates is in 2 dimensions, we have 2 variables. We have a radial variable, and then we have a variable which varies on the circle. That's the angular variable. In 3 dimensions, we have a variable, and we have a variable which varies on a 2-dimensional sphere. And in 4 dimensions, we have a radial variable, and which varies on a from 0 to infinity, and we have a spherical variable which varies on a sphere. So in d dimensions, if you go into where this is the d minus 1 dimensional sphere, and so this is equal to the integral over the d minus 1 dimensional sphere, d sigma. Now, sigma is just how you parameterize the sphere somehow. I mean, in 3 dimensions, we use theta and phi. Of radius 1 times the integral from 0 to infinity e to the negative pi r squared times r to the d minus 1 dr.
Professor, what is the outer integration over? Is it s to the d minus 1?
S to the d minus 1, right?
Ah, I see. Okay.
D minus 1. Sure. Okay. So who remembers the definition of the gamma function?
I do. I think I do.
Okay. So gamma of x is the integral from 0 to infinity t to the x minus 1 times e to the negative t dt, right? I think that's it. Okay. So we have the integral over sd minus 1 d sigma. This is the surface area of a sphere of radius 1 in d minus 1 dimension. And then we have the integral from 0 to infinity. Utah, be quiet. R to the d minus 1 e to the minus pi r squared dr. Is it the right formula?
Yes,
Gamma
sir.
function.
Uh-huh.
Okay, so we make a change of variables. T equals pi r squared. dt is equal to 2 over pi r dr. Are you following me so far?
Yes, yes.
So this is let me call it the measure of sd minus 1. That's the integral over the sphere times the integral from 0 to infinity e to the negative t dt. We need a pi here because of the 2 over pi, and we need a 2 here. And then one of the r's goes away, so we have r to the d minus 2. So this follows that r is t over pi to the 1/2, and so we have t over pi to the 1/2 to the d minus 2 over 2.
Mm.
So if we put that all together, we get the measure is equal to times pi over 2, and then we have down here a pi to the d minus 2 over 2 from here, and we get integral from 0 to infinity t to the d over 2 minus 1 e to the negative t dt, and this is equal to gamma of d over 2.
Mm.
I hope I got that right.
Mm.
So this is the measure of the d minus 1 dimensional sphere is pi over 2 times pi to the d over 2 minus 1. This now becomes a minus.
Here, I think here this one should be the other way. This one, 2 pi r dr.
R is t over pi, right? Oh, so right.
Mm-hmm.
So there should be another pi down there. There should be a pi to the negative 1. And then the pi to the negative 1 here cancels with this negative 1.
Mm-hmm.
And then we have a gamma of d over 2.
Mm-hmm.
And we put all this together to find the measure of the d minus 1 dimensional sphere is equal to gamma of d over 2 no, it's 1. Let me take that back. It's 2 pi to the d over 2
Yes.
divided by gamma of d over 2.
Mm-hmm.
Because everything is equal to 1, right?
Yes.
Okay. And then we can continue to look at the unit ball. So B1 around 0 in d dimensions is a set of all x such that absolute value x is less than or equal to 1. This is equal to the integral from 0 to 1, and the integral over S d minus 1 over d minus 1 dimensional sphere, and you get r to the d minus 1 dr, and then d sigma. The d sigma integral just integrates up to what we just got, pi over d2 divided by gamma over d over 2 times the integral from 0 to 1 r to the d minus 1 dr, which is r to the d over d. And if you evaluate it at 0, you get 0. And if you evaluate it at 1, you get 1 over d. So pi to the d over 2 over gamma to the d over 2 times
Plus 1.
1 over d, right?
And then d
And now
is gamma 1.
no, but gamma of d times d, d over 2 times d is gamma of d over 2 plus 1.
Mhm.
That's the functional
Definition. Yeah.
the functional equation for the gamma function, and I just, so this whole thing is equal to pi to the d over 2 over gamma of d over 2 plus 1. And that's the volume of the unit ball in d dimensions.
Mm. Professor, there's a 2 missing in the second equality. This one,
In which one?
right here.
Is there 2 missing?
Yes.
Of course there is.
Mm.
But wait, where do I get rid of this 2?
Mm. I don't know. So, Professor, the D and the D, we get the plus 1 because it's the same D, or?
It's the same d, yeah.
Yes, yes, okay.
But gamma of x plus 1 is x times gamma of x.
Mm. Yes. Thank you.
Oh, that's where the 2 goes away, because we have a d over 2. Because we don't have x times gamma of x, we have d over 2 times.
Mm.
So we have a 2 down here,
Mhm.
which gets rid of this 2.
Mhm.
Now, but this is a very nice way of showing that this is the volume of the unit ball. The other way of showing it is doing this multiple integral. 1 minus
I don't want to do.
x1 squared plus xd minus 1 squared dx1 up to dxd minus 1, and you integrate that over a unit ball in d minus, so this is a d minus 1 dimensional unit ball. That's how I learned it in calculus. Was a kid. And then you use induction.
Oh
But
my
using
goodness.
this, using polar coordinates and using the fact that this that the total weight of a unit normal distribution is 1 in any dimensions. That's what part A says.
Okay.
You can quite easily compute the volume of a unit ball in any dimension by just using that fact.
Oh.
Okay, I think that's it for today.
Can it be extra credit, Professor, if we do the long way?
That was a that was a possible homework assignment in chapter 2, which I spared you of.
Thank you.
If you want extra credit, I put it on the final.
Oh, okay, sure.
Wow.
Thank you. I need every single. I'll work like a dog.
But I tell you the truth, I do not want to correct this problem. Because it's a royal mess. So that's it for this semester. No more reading. I'm gonna put the final up tomorrow on Canvas, and I ask you to upload it on Canvas. because then I can use the speed grader. Not that it's any faster than the slow grader at home, but but we're gonna have a meeting on Wednesday. You can ask me questions about the finals if you have any, and I just want to have your input. What do you think about this whole online business?
I miss seeing face-to-face interaction in class.
Well, you can turn your video on.
Yes. But it's different, Professor. It's different, person like in the same classroom with a chalk dust flying all over the space, and I don't know.
Well,
But yeah, it's a second best to having an actual meeting. But I feel safe from coronavirus, so it's I cannot complain.
yeah.
Professor, do you mean in general of like how we feel about online classes, or in this specific situation?
Well, the specific situation, because none of us signed up for an online class, right?
Right. I think it feels different because there's like less accountability. I feel like when there is when you have to see a professor, like you prepare ahead of time to make sure you get all your questions in and all that stuff. But with online, you can relax a little because you're like, oh, okay. If I have any questions, I would just, I will ask them at any point in one of the online lectures. So it's the accountability level is not as intense as it is when you're in class, which makes it harder.
I agree. That's part of it. And I mean, the thing is, even little things like attendance or something like this, I can see the participants who are there. You're all there, but I don't know whether you're all there.
Mentally,
right? You might be
Right.
in the kitchen cooking supper, and that's a valid reason not to be there. But you might listen around to it. So that's one way. There's less accountability.
That's true.
And the other thing is, even if we have the video on, none of us is trained to talk the right way into a camera. If you look at people who are doing TV for a living, and they're all on these Zoom meetings nowadays, in these discussions on the news and stuff like this, but they know where to look in it to make it okay on a camera. To be, but we're gonna stay all over the place. At least I will.
That's true. And then with a wine glass on the left-hand side, bottle on the shelf.
Yeah, right, right. That's I mean, it's disturbing, but it is. You can make an online class more accountable. For that, you have to be told a semester ahead of time that you're teaching online. I mean, I think Angela, you have the same thing in your labs, right?
Yes, sir.
It's anyway. So we'll have a meeting on Wednesday. You can ask questions, and but no more reading, no more homework assignments, just the final.
Yay.
Yes. Thank you, Professor, for the semester.
I will adjourn the meeting.
Thank you,
Yeah.
Professor.
And
Thank you,
no
Professor.
more
Thank you.
Zoom